Welcome to the video lecture series for Texas A&M University Course Math 152. Today we will look at section 8.9 Improper Integrals. You can find the accompanying handouts at bit.ly/Raelene Math 152. Let's begin. As a warm-up, we're going to evaluate the definite integral from 1 to 4 of dx over x minus 2 and explain the result graphically. So, we could use a method of substitution because we have an inner function, and so we could let t equal x minus 2, so that dt is equal to dx, and when x is equal to 1, we see that t is equal to negative 1, and when x is equal to 4, we see that t is equal to 2. So therefore, the definite integral from 1 to 4 of dx over x minus 2 is equal to the definite integral from negative 1 to 2 of dt over t. So we get the ln of the absolute value of t evaluated from negative 1 to 2. We get the ln of absolute value of negative 1 is the ln of 1. Sorry, we put the 2 in first, the top bound. So we get the ln of absolute value of 2 minus the ln of absolute value of 1. And the ln of 1 is 0, so we get the ln of 2. Now, to represent this result graphically, let's take a quick look at the graph of 1 over x minus 2. This graph has a vertical asymptote at x equal to 2, and a horizontal asymptote still along the x-axis. And we can see a y-intercept when x is equal to 0, y is equal to negative 1/2, and we get a graph that looks somewhat like this. It's a transformation of the basic 1 over x graph. And we are looking at the graph, the indefinite integral from 1 to 2, 3, 4, and so we are coming up with something that is a little bit strange. We see a definite integral as accumulation or directed area, and from 1 to 2 we are going to have an infinite amount of area. From 2 to 3 we're going to have an infinite amount of area. So looking at the accumulation of this function, it seems that we're having some problem over the vertical asymptote of x equal to 2. And in fact, before we do any calculus or integral with the function, we need to consider that the domain of the function is that x cannot be equal to 2, and therefore the bounds from 1 to 4 are a problem. So this may not in fact be the correct answer. We should explore this a little more carefully because we are getting infinite amount of sub-integrals if we were to separate from 1 to 2 and 2 to 4. So let's proceed. This section on improper integrals will tell us what happens if we have a vertical asymptote in the integrand function. In number 2, determine the domain of the following functions and their derivatives and state what kind of discontinuity exists in each case, if any. So we have the graph of 1 over x, and I've got a very small grid here. So we have our basic odd multiplicity vertical asymptote. The domain of this function is x contained in the reals, but x not equal to 0. And when x is equal to 0, f of 0 is undefined. And there undefined means non-zero over 0, and so therefore there's a vertical asymptote at x equal to 0. F prime of 1 over x is going to be negative 1 over x squared, and so we are going to get a vertical asymptote of even multiplicity with a vertical reflection. The graph of 1 over x squared is going to look. Each branch is quite similar, but we'll see that because we're squaring the values, the heights for the same x values will not be the same y coordinates. On a bigger graph, maybe making a table of values, you could really see the difference between the amount of flattening of the original 1 over x compared to the derivative negative 1 over x squared. The domain of this function is still x not equal to 0. And when we describe f prime of 0, we still get undefined, but we get a vertical asymptote of even multiplicity here because of the exponent 2 making there be no sign change in the output value for f prime on either side of x equal to 0. Okay, in the second case, y equals the absolute value of x. Make sure you're getting slopes of 1 and -1 on either side here. The domain is x contained in the reals. And f of 0 is equal to 0. We actually have an x-intercept and a y-intercept. The derivative of the absolute value of x is absolute value of x over x. And that function is the basic jump discontinuity. And the domain of this function is all reals except 0. And f prime of 0 is indeterminate. And therefore we have either a jump or a hole. Because the limit as x approaches 0 on this graph does not exist, because we have a different left-hand limit from the right-hand limit, even though the left and the right-hand limits are both finite, we have a jump. We can't really say we have a jump at a specific point. We just have a jump when x is equal to 0. The graph of y equals x to the 2/3 is a typical cusp, and I'm going to draw this graph. It's not very accurate. It needs to have even symmetry. It's not accurate because my grid is very, very small, but you could plot a table of values and come up with some specific points. An easy point to substitute in would be x equal to 1, because the cube root of 1 is 1, squared is still 1. We can also substitute x equal to 8. The cube root of 8 is 2, squared is 4. And we have the domain is all real numbers, and f of 0 is equal to 0 in this case. The derivative of x to the 2/3 is 2/3 x to the -1/3, and x to the -1/3 is going to give us a vertical asymptote at x equal to 0, and we have odd multiplicity. So again, we have a shape that looks like 1 over x, but the exact values for y for each x value will be different because of the coefficient and the exponent. So a table of values would give you more accurate y coordinates. The domain is all reals except for x, and f prime of 0 is undefined. We have a vertical asymptote of odd multiplicity located at x equal to 0. The odd multiplicity, again, is going to give us the change of sign over the x equal to 0 root of the denominator. And lastly, we have the cube root of x. This is the inverse of the x cubed function, and it is a classic example of a vertical tangent at the origin. The domain is all reals. F of 0 is equal to 0, but the derivative graph, or the derivative function, is 1/3 x to the -2/3, which is going to be a vertical asymptote at x equal to 0, which is our domain restriction. And we are going to have all positive y values, so it's going to look more like the -1 over x squared graph. The reason we have even multiplicity here, or even behavior, is because of the squaring from the numerator of the exponent around the cube root of x. So we're going to have something that looks like this. Again, the exact flattening or heights of the y coordinates depends specifically on the table of values created from this expression. If we make a table of values for x and y, the y values here would be different numbers from the y values in any of the other graphs. In number 3, determine the average rate of change of g of x on the interval from 1 to 4. Well, when we look at this, we notice average rate of change is going to be a secant slope. And so we would look at g of 4 minus g of 1 all over 4 minus 1. And g of 4 is going to be 1 over 4 minus 2, which is 1/2, minus 1 over 1 minus 2, which is -1. Let's see that again. 1 minus 2 is -1. 1 over that is -1. All over 3, and so we will get 3/2 over 3, which is 1/2. And then if we take a look at part B, the secant slope is going to be g of 2 minus 1 all over 2 minus 1. And so when x is 2, y is undefined. And we see that that's a bit of a problem because undefined on this graph is either going to be positive or negative infinity for the y value, so we can't work this out. So this expression, this value does not exist because we have undefined in the numerator. So the question asks, or is really pointing out the difference between part A and B. we could come up with a finite number when the interval was from 1 to 4, but we couldn't find a finite number when the interval was 2 to 4. Because the endpoints of the first interval did not indicate the domain restriction, namely that x cannot equal to 2, if we simply calculate g of 4 and g of 1, no problem arises. But we do have to pay attention to the domain restriction and the fact that the domain restriction x equal to 2 is inside this interval. That essentially makes the first calculation impossible. So the major point of the warm-up questions so far is to consider the domain of the function before proceeding with any calculation. So in number 4, we're wondering what is the difference between a vertical asymptote and a non-vertical asymptote, such as slant, horizontal, parabolic asymptotes, etc. A vertical asymptote is a finite x value that makes y undefined. And in order to make y undefined, we would say that y is non-zero over 0, or we would say that y approaches positive or negative infinity for that finite x value. Meanwhile, a non-vertical asymptote is the end behavior asymptote, or the zoomed out behavior of a function. And when we talk about the zoomed out behavior means that x is approaching plus or minus infinity. So we would specifically get a horizontal asymptote if y approaches a constant when x approaches plus or minus infinity. Let's just take a quick look at some pictures. If you've never seen this before, it will be very helpful to do so. So we look at a vertical asymptote in the case of 1 over x minus 2 occurring at x equal to 2. The denominator value, or the value rather for x, that makes the denominator 0, but the numerator not 0. Let's contrast that with y equal to x minus 2 divided by x minus 2. In this case, the red function, we see that x equal to 2 makes the denominator 0, but it also makes the numerator 0. And 0 over 0 is not undefined. As we can see, in this case, we do not have a vertical asymptote. What we do have is a hole in the graph. You can refer to the pre-calculus videos 2.6 rational functions on the pre-calculus or Math 150 page for more information about rational functions and their different types of discontinuities. Well, if we want to look at the end behavior, let's consider a function written even just x squared plus 3x minus 4. When we zoom out on this function, it looks like a parabola. But what we might not realize when we think numerically is that as x approaches plus or minus infinity, the leading ordered term dominates the numerical value of the other two terms. And so while when we look at a 1-by-1 scale of these two graphs, they don't look alike at all. But if we zoom out, eventually these two graphs look very, very alike. And so if we are looking for the blue graph to be modeled or approximated by a simpler monomial one-term function when we zoom out, when we let x approach positive or negative infinity, we can see that x squared is a good approximation for x squared plus 3x minus 4, even after x is approaching even 100 or 200. The purple expression is a good approximation for the blue expression. In the case of rational functions, if we look at y equals x, let's say y equals 3x minus 1 plus 1 over x plus 4, we do have a vertical asymptote at x equal to -4. But if we zoom out, eventually we see that this graph looks like a line. And not just any line, this graph is specifically going to look like the line y equals 3x minus 1, because as x approaches infinity, this denominator approaches infinity, or negative infinity, so the denominator will approach negative infinity, which means that the entire fraction, 1 over x plus 4, will approach 0. And so y is going to approach 3x minus 1 plus 0, so y will approach 3x minus 1. In a not zoomed out scale, these two graphs don't really look alike. But eventually, if we zoom out far enough, well, let me start again. If we zoom out far enough, these two graphs do look alike, and we can't tell the difference when x is 100 or 500 between the blue expression for y and the purple expression for y. And so what we see is that 3x minus 1 is a non-vertical asymptote. In other words, it's the value or the function or the formula that the y-coordinates will take on or approach as x approaches plus or minus infinity. In number 5, we want to consider the basic vertical asymptote function or infinite discontinuity function, y equals 1 over x, just for x contained from 0 to infinity on an open interval. So we'll sketch the function. So when x is 1, y is 1. When x is 2, y is a half. When x is 1/2, y is 2, and so on. We know that when x is 0, y is undefined. So specifically, as x approaches 0 from the right, y approaches positive infinity. And so we have our function. And we want to know the graphical significance of the definite integral from a to b of dx over x. Well, this represents if a is less than b, then we are reading the graph or the definite integral from left to right. And furthermore, since 1 over x is positive, let's say that a is more than 0. So if we're taking a segment of the graph like this, where this is a and this is b, we have a positive width, we have positive height. So this integral represents the area under the curve from x equals a to x equals b. Now let's evaluate the limit as a approaches 0 of the definite integral from a to 1 of dx over x. Well, the first thing we do is work from the inside. And so we have the definite integral is going to be the ln of x, ln of absolute value of x, evaluated from a to 1. And we wait for the limit until after the integration has been done, and now the evaluation has to be done. So the limit as a approaches 0 of the ln of 1 minus the ln of a. And we're going to be taking a and b to be greater than 0. So we don't need the absolute value signs around a. We know that the ln of 1 is equal to 0. And so we have the limit as a approaches 0 of negative the ln of a. Now, if we consider looking at the graph of ln of a, I'm going to take this negative sign in front. The graph of y equals ln a, where we have the y-axis and the a-axis. We know that a can only approach 0 from the right, because the domain restriction on powers is that powers must be positive. And so if this is the case, we see that as a approaches 0 from the right, the y-coordinates on the graph of ln a approach negative infinity. So this value approaches negative infinity, and negative infinity equals positive infinity. We could repeat the process for part D, where we let b approach infinity. So if we do that, we have the limit as b approaches infinity. We can work out the definite integral to be the ln of x in absolute values, evaluated from 1 to b. And so we get the limit as b approaches infinity of, again, b is greater than 1 or greater than 0. So we will take, because b is approaching infinity, we know that it is bigger than 1. so we don't need the absolute values around b. Again, the ln of 1 is 0. And now if we use the graph of ln of b, well, we could make this the graph of ln of b if we prefer. And as b approaches infinity, the height on that graph very, very slowly, but definitely approaches a height of infinity. And so this limit is equal to infinity. So what we're seeing is that the graph of f is not the graph of ln x or ln a or ln b. The graph of f is the graph of 1 over x. And what we are talking about is the area under 1 over x from x equals a to x equals b. Well, if a is approaching 1, then we have an infinite amount of area. And if b is approaching infinity, then we have an infinite amount of area. So the infinite amount of area, according to a approaching 0, is this infinite green strip here. And then we're talking about b approaching infinity, so we have an infinite amount of area working horizontally. So in the first green case, we have the height of the f graph. The y-coordinates are approaching positive infinity. And in the blue shaded region, we have that x is approaching positive infinity. So we're finding that the definite integral does not exist. In number 6, let's ask a question about a two-dimensional region. Can it have an infinite arc length, or perimeter, while at the same time having a finite area? Well, this question has its roots in what we call fractal geometry. And I'm going to give you an example of a Koch curve, or the Koch snowflake. And we can take a look at some different iterations here. If we start off with an equilateral triangle, we can develop this curve that has a longer and longer perimeter, or larger perimeter values. We cut this each side into 3 equal pieces, and then we create another equilateral triangle in the middle. If we do that again, we take this piece, for example, and we recursively or repeatedly create the same pattern. If we do this over and over and over again, we see that we are going to get a longer and longer perimeter. The idea of the Koch snowflake is that this can be done infinitely many times, and therefore the resulting curve, called the Koch snowflake, will have an infinite length. However, since I can draw that snowflake inside of a box that has finite area, it is possible to get an infinite length with a finite area. We know that the area of the actual snowflake is going to be less than the area of the box that contains it. And we can go to a website. We can go to Wikipedia and take a look at, if the link wants to work. It doesn't, but you can check this website out. Let's do it now. It's a rather interesting visualization. Here we go. And we can see there are the pictures that I just took. And here's the Koch snowflake. If we started at the very beginning equilateral triangle, the iterations show longer and longer arc length or perimeter, but it's still contained within this box. And we call this type of geometry, where you zoom in and it looks the same as when you zoomed out, as self-similarity. And this is the nature of chaos theory. So the answer is yes. A 2D region can have infinite arc length while at the same time having finite area. So to continue on with this exploration of this idea, we're going to put the correct inequality sign in the box here and explain. The definite integral from 1 to 10 of the absolute value of a function plus 1 dx is what size? Greater, equal, less than? The definite integral from 1 to 10 of the absolute value of a function dx. The reason we're talking about the absolute value of a function is just to ensure that the height is not negative. And so since we have the lower bound smaller than the upper bound of the definite integral, we know that we have positive width and positive height, and therefore each of these definite integrals can be thought of as the area under the curve. Well, what we know is that the absolute value of f of x plus 1 is a vertical translation, so it's one higher than the graph of absolute value of f of x. And so if I have some curve f of x like this, who's, well, in absolute value, then I know that one more than that will look like this. And so as a result, the definite integral from 1 to 10 of the red curve will be greater than that of the blue curve. So now we're ready to really put all of these ideas and obstacles into 8.9, improper integrals. Any definite integral in which either an x-coordinate or a y-coordinate of an integrand, which is the function to be integrated, if either the x or the y-coordinate goes to plus or minus infinity, we have a definite integral which we call an improper integral. Improper integrals either converge, and therefore they have a finite value, or they diverge and they do not exist because they do not have a finite value. So some examples are the integral from 0 to infinity of e to the negative x dx. We see here that as x approaches infinity, we have the x-coordinate going to infinity is going to give us an infinite length of the interval. We're going from 0 to infinity along the x-axis, so we have an infinite length. But as we just talked about with the Koch curve, it's possible that we have a curve with infinite length but finite area. So even though the definite integral bounds are infinite in length, or the interval along the x-axis is infinite in length, it is possible that the area, or the accumulation, does exist. Similarly, in the second example, we have the x interval is going from negative infinity to positive infinity, and we definitely have some infinite length here. We also know that as x approaches negative infinity, e to the negative x is going to be the same as e to the infinity, which is infinity. So not only are the x-coordinates approaching infinity, but the y-coordinates at the end behavior will be approaching infinity. Just the left end behavior, though. In the case of the integral from 1 to 4, we see that we have a finite interval, that the interval along the x-axis is only 3 units long. So the x-coordinates are not going to plus or minus infinity. So the width is not infinite. But we notice that we have a vertical asymptote at x equal to 2. So there is a finite x-coordinate that makes y infinite, and therefore this is an example of an improper integral. And similarly, the last definite integral has an x-coordinate of 2, which is restricted from the domain because it produces a vertical asymptote. But we also have an infinite width, or interval along the x-axis. So this last integral is really badly improper because not only does the y-coordinate approach infinity, or negative infinity, as x approaches 2, but we also have the interval is an infinite length, as opposed to the finite length that we had in the third one. So, improper integrals with infinite bounds, we are going to proceed by changing the improper integral into a proper integral with a bound of t, and we are going to evaluate the limit. If the limit is finite, then the improper integral converges, and we can say that the value of the improper integral is whatever the limit value worked out to be. But if the limit is infinite, does not exist, then the improper integral does not exist either, and we say that the integral diverges. So when we have f continuous from a to infinity, then we are simply talking about the x bounds being plus or minus infinity. These are not cases with a vertical asymptote, because we are saying that f is continuous and a vertical asymptote is an infinite discontinuity. So let's take a look at some examples. We have the function from 1 to infinity of 1 over x is defined from 1 to infinity. So it does not hurt to draw a picture of the graph. We have the graph of y equals 1 over x. We know that we have a vertical asymptote at x equal to 0, but we are interested in starting the definite integral at 1. And so we are looking at the accumulation, or the definite integral, from 1 to infinity. Well, we know that the length of the integral, or the interval, is from 1 to infinity. It's an infinite length. But we are wondering if it's possible to have finite amount of area. So what we do is we change the integral to a limit where t approaches infinity, which is the offending x-coordinate in the bound. From 1 to t, we have the integral of 1 over x dx. So we work from the inside out. We save the limit to the last. The limit as t approaches infinity of the ln of absolute value of x evaluated from 1 to t. So we save the limit, work from the inside out. We did the antiderivative. Now we must do the evaluation. Since 1 and t are between 1 and infinity, we don't need the absolute values, and we get ln of t without absolute value minus ln of 1. The ln of 1 is 0, and then we can evaluate on the graph of ln of x or ln of t. So if y is equal to the ln of t, as t approaches infinity, the height of the graph approaches infinity. And so we know that this limit is equal to infinity. In other words, the amount of green area, and I can call it area because I have positive width and positive height for this graph on this interval, and so this is an infinite amount of area. And so we say that this definite integral diverges or does not exist. There is not a finite accumulation. In number 9, try it by yourself, and you can pause the video and check in with me in a moment. Here we change the improper integral to a limit as t approaches infinity, of the integral from 1 to t, e to the negative x dx. Keep the limit for the last, perform the antiderivative, which is negative e to the negative x, evaluated from 1 to t. Again, we should always think about the graph. It's very helpful for visualization, and we know that the graph of e to the negative x is exponential decay. And we're looking from 1 to infinity. So we're looking for an infinite length curve that goes on from 1 to infinity for an infinite amount of x-coordinate. We want to know, is the red amount of accumulation finite? And the accumulation has positive width times positive height on this portion of the graph, and so the accumulation is the same as the area under the curve. So continuing on here, we get the limit as t approaches infinity. I'm going to change the sign and swap the bounds. And so I'm going to get e to the negative 1 minus e to the negative t. And I can distribute my limit through. I'm going to get 1 over e minus the limit as t approaches infinity of, I'm going to rewrite this, I'm going to leave it actually as e to the negative t. And now I'm going to think of this graph in red. This graph was y equals e to the negative x. So it's actually the same graph. And on this function, as t approaches infinity, y approaches a height of 0. So this limit is equal to 0, and we end up getting a finite amount of area in the original red shaded. So we say that the integral converges, and we can simply say that the integral from 1 to infinity of e to the negative x dx is equal to 1 over e. So the amount of area here, because we have positive width and positive height, the definite integral is the same as the area. So the amount of area is 1 over e. So again, we have an infinite length curve, but we have a finite amount of area. In number 10, we are going to look at the definite integral from negative infinity to infinity. In this case, we have to set up a limit as t approaches infinity, and we can take the definite integral from negative t to positive t of dx over 1 plus x squared. Now the graph of 1 over 1 plus x squared is what we call the normal distribution. It's a rational function, but it has no vertical asymptotes because we have no possibility of the denominator being 0. And we are looking for the amount of accumulation from negative infinity to positive infinity on a positive height graph. So we're looking for the green accumulation, which is the same as the green area. We have an infinite length curve. Do we have an infinite amount of area? Well, let's work out the limit to find out. Before we work out the limit, we have to work out the definite integral, and we see that the function 1 over 1 plus x squared has even symmetry. Because the function has even symmetry and I have a symmetric integral, I can change, or interval, symmetric interval, I can change the integral to 2 times the definite integral from 0 to t of dx over 1 plus x squared. And I can take the 2 in front of the limit, and I know that the antiderivative of 1 over 1 plus x squared is tan inverse of x from 0 to t. So this gives 2 times the limit as t approaches infinity of tan inverse of t minus tan inverse of 0. So we're going to take a look at the graph of y equals tan inverse of t. The function has horizontal asymptotes wherever the tangent graph had vertical asymptotes on the restricted domain. Namely, these are y equals positive pi by 2 or y equals negative pi by 2. The graph passes through the origin and is an increasing function, increasing but bounded. And so we know that tan inverse of 0 is 0. And we can see that as t approaches infinity, y on this graph approaches a height of pi by 2. And so we get 2 times pi by 2, which is equal to pi. And so the amount of green area, and I can call this integral area because we have positive height and positive width. Even though we have infinite length, we have a finite amount of area, which is pi. Number 11 asks to discuss the convergence of integrals of the form integral from 1 to infinity of dx over x to the p. And the question asks, for what real values of the constant p does this integral converge? So we're going to rewrite the definite integral from 1 to infinity of dx over x to the p as a limit as t approaches infinity of the definite integral from 1 to t dx over x to the p. And I'm going to write 1 over x to the p as x to the negative p. So we get the limit as t approaches infinity of the antiderivative, which is x to the negative p plus 1 over negative p plus 1, or 1 minus p, evaluated from 1 to t. So this works out to the limit. Well, in fact, 1 minus p is a constant. It's a finite constant as long as p does not equal to 1. So I'm going to take that 1 over 1 minus p in front of the limit with the stipulation that p cannot equal to 1. So we definitely know that p is not allowed to equal to 1 if we want this integral to converge. Now let's continue on. We have 1 over 1 minus p is constant times the limit as t approaches infinity of t to the 1 minus p. And don't forget that x is the variable that we are substituting the bounds in for. So t to the 1 minus p minus 1 to the 1 minus p. Now, as long as p doesn't equal to 1, 1 minus not 1 is a constant that's not 0. Either way, 1 to that exponent will be 1, and so we are going to get a 1 from here. Furthermore, we can break this apart, and we can get 1 over 1 minus p times the limit as t approaches infinity of t to the 1 minus p minus 1 times the constant, or times the factor out front. And now we need to focus on this limit. Well, let's think graphically about this piece. If we consider the graph, if we consider different values here of p, if p is going to be a positive number, but greater than 1, then this exponent is going to be a negative number. And t to a negative number has a graph of, for example, if p is equal to 2, which is a number greater than 1 for p, then we get t to the 1 minus 2, which is t to the 1, and we're going to get a graph that looks like this. So this is the graph of y equals t to the 1 minus p if p is greater than 1. At least we'll either have another portion of the graph over here or down here, depending on what kind of number p is. But we're only focusing on from 1 to infinity, so we don't need to consider negative values for t. So if p is greater than 1, the graph will look like this, and as t approaches infinity on this graph, y will approach a height of 0. However, if we have y equal to t to the 1 minus p, where p is less than 1, again, we don't have to consider p equal to 1 because the denominator was not allowed to be 0, so p is not allowed to be 1. If we take a look at a graph like this, we could pick a value for p like 0 or negative 1 or negative 2. If p is 0, then we get t to the 1 minus 0 is t to the 1. If p is, again, we also don't need to look at the negative values because we are only going from 1 to infinity in this definite integral. So if p is negative 1, we get y equals t squared. If t equals negative 2, we get t cubed, and so on. For all of these power functions, as t approaches infinity, y approaches a height of infinity. If we want this red limit to exist, then we don't want y to approach infinity, so we don't want p to be less than 1. So we want p to be greater than 1. And if p is greater than 1, this limit will equal 0. And as a result, the final answer is going to be negative 1 over 1 minus p, which is the same as 1 over p minus 1 for p values that are greater than 1. So at this point, we should really look at some different graphs. If we consider the graph y equals 1 over x as kind of a baseline graph, what we're considering is looking when x is greater than 1 and to see how much area we have, because we can talk about area. We have positive width and positive height on that domain. And so we have an infinite length of graph, but we are saying that we will not have a finite area, because when p is equal to 1, we're going to have 1 over 0, which is undefined, and therefore the limit will not exist. But what happens when p is equal to 2 or 1/2? Let's consider two other possible cases of the graph. Y equals 1 over x squared when x is greater than 1, and y equals 1 over x to the exponent 1/2 when x is greater than 1. And so if we look at these three graphs, we can see that the blue graph is the baseline graph, under which we will not have a finite amount of area, because we're going to get 1 over 0 multiplied by the rest of the limit. However, if we have the red function when the p exponent on x in the denominator is 1/2 or less than 1, we see that the red graph is higher than the blue graph. If the blue graph does not have a finite amount of area, then a graph that lies above it also does not have a finite amount of area. Meanwhile, the purple graph lies below the blue graph and therefore does have a chance of having a finite amount of area. And so this is actually consistent with our results. We know that when p is greater than 1, such as in the case of the purple graph, we are going to get a finite amount of area, or a converging finite improper integral. And specifically, since p is equal to 2, the amount of area under the purple curve will be 1 over 2 minus 1, which is 1. Now we should maybe take a look at the reciprocal functions. When we look at the graphs of y equals x, y equals x squared, and y equals the square root of x, or x to the 1/2, and I think I'm just going to make them the similar colors. So this one is blue, this one is purple, and this one is red for being the reciprocals of the graphs we just saw. And let's just focus on x greater than 0 for a moment. When x is greater than 0 for each of these functions, which is practical for the square root function because the domain has to be non-zero, the x values, we see that when x is equal to 1, all three of these heights or expressions are equivalent to 1. When x is greater than 1, the purple function, y equals x squared, is higher. The blue function, or y equals x to the 1, is the middle, and the square root of x is lower. So the square root of numbers greater than 1 are smaller than the input number of x in the first place. Meanwhile, between 0 and 1, the heights of the graphs reverse. We see that the square root of x is the highest and the x squared graph is the lowest. Knowing these three graphs will help us to come up with this result because we are taking the reciprocal of the y values, which reverses the behavior from 1 to infinity along the x-axis. Okay, let's continue on. Integrands with infinite discontinuities. We just looked at infinite length intervals, and therefore we were talking about x approaching positive infinity or negative infinity or both. Now we are going to consider that y approaches plus or minus infinity, which means that we have a vertical asymptote in the function. So, and of course it's important to notice that the vertical asymptote has to occur on the interval of the definite integral. It's possible that we could take a function like 1 over x and find its definite integral from 1 to 7. The vertical asymptote does not occur between 1 and 7, and therefore this is not an improper integral. So, if the y value becomes infinite at some point, we can replace the offending x coordinate with t and proceed as we did in the previous examples. So let's say that f is continuous on a to b, but at a there is an infinite discontinuity or a vertical asymptote in the function. In other words, f of a is undefined, which is non-zero over 0, not to be confused with 0 over 0, which is indeterminate. Then we proceed by letting t approach a from the right, because we have the interval from a to b like this, and a is a one-sided direction. x can only approach a, or t can only approach a, coming from the right. Meanwhile, if we have a vertical asymptote at x equal to b, then we're going to let t approach b from the left, and then we replace the b with the t. If the limit is finite, we say that the improper integral converges, and the value of the limit is the value of the improper integral. Otherwise, if the limit is infinite, the improper integral diverges. Furthermore, if we have the vertical asymptote occurring at x equal to c, which is in between a and b, then we have to split up the integral into two integrals where we have t approaches c from the left and t approaches c from the right when we take the limit and turn it in, the integral and turn it to a limit. If one or both of the integrals diverge, we say that the original integral also diverges. Let's consider an example. We have an infinite discontinuity at an x value that is interior to the integral bounds. And we saw this function earlier. 1 over x minus 2 has a vertical asymptote at x equal to 2 because f of 2 is undefined. And because of the sign chart, we know that as x approaches 2 from the left, y is going to approach negative infinity. And as x approaches 2 from the right, y is going to approach positive infinity. Okay, we are going to look at the integral from 2 to 4, which is not a finite, an infinite interval. So we don't have an infinite length of curve, except when we look at this, the curve is going up, 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 up. We actually do have an infinite length of curve. We just don't have an infinite width. We have an infinite height. And so we are coming up with the definite integral by breaking it apart at the offending x coordinate. We know that the domain says that x cannot equal to 2. So we first break this integral up as the integral from 1 to 2 of dx over x minus 2 plus the integral from 2 to 4 dx over x minus 2. And then we say the limit as t approaches 2 on this first region, t is going to approach 2 from the left. So we put t is approaching 2 from the left of the definite integral from 1 to t of dx over x minus 2 plus the limit as t approaches 2 coming from the right of the definite integral from t to 4 of dx over x minus 2. Now we did this integral in the warm-up, so we know that the method of substitution will give us the ln of x minus 2. So now we keep the limit ln of absolute value x minus 2, evaluated from 1 to t, plus the limit as t approaches 2 from the right, of the ln of absolute value x minus 2, evaluated from t to 4. Well, we can take a look at the graph of ln of absolute value of x minus 2, and let's put it on the next page. The ln of absolute value, ln of x minus 2, is going to look like the ln of x graph translated 2 spaces over, and the ln of absolute value of x minus 2 is going to look like a mirror image. So this is actually at x equal to 3. Doesn't look very good there, very symmetric. But if you don't believe me, you can make a table of values. And we can just take a quick look in the graphing program to confirm. Y equals the ln of x, first of all. Y equals the ln of x minus 2. And y equals the absolute value. Okay, so we have that graph, and we see that we have the x-intercepts at 1 or 3. And now we are going to interpret as t approaches 2 from the left on this graph. As t approaches 2 from the left, y approaches a height of negative infinity, same as t approaches 2 from the right. So we will expand this, the limit as t approaches 2 from the left of ln of absolute value of t minus 2 minus ln of 1 minus 2 is negative 1, absolute value of 1, negative 1 is 1, and the ln of 1 is 0. And I'm just actually going to write the second limit in blue to make it easier to see. The limit as t approaches 2 from the right of, this becomes the ln of 4 minus 2, which is 4, minus 2 is 2. So the ln of 2 minus the ln of absolute value of t minus 2. And we know that this limit is going to approach negative infinity, this limit is going to approach negative infinity, and therefore we have negative infinity does not exist. And so even though it looks like we have some symmetric amount of area, that this green area and this green area are the same but opposite, we don't get to cancel them out. Rather, hold on a minute. Let's just make sure that this is actually complete rather than confusing you. We have the limit of this is going to be ln of absolute value of t minus 2 minus 0 plus ln of 2 minus the limit as t approaches 2 from the right of the ln of absolute value t minus 2. And so we might wonder, can we just cancel out? I'm going to put this ln of 2 in green. Can we just subtract the red minus the blue and get 0? Because what we have here is infinity, negative infinity here, plus ln of 2 minus negative infinity. And so negative infinity plus infinity is 0, or so we might think. But recall that infinity minus infinity is actually indeterminate, and we would have to use some method from Calculus 1 to determine it. However, that's not necessary in this case, because in the previous slide we saw that if either of the individual integrals diverges, this one or both, then we say that the original integral diverges. So we have that this integral does not exist, diverges. So we cannot combine negative infinity plus infinity to get 0. Okay, in the next example, we have the definite integral from 1 to 4 of dx over x minus 2 to the exponent 2/3. So we are going to rewrite this, breaking it apart at x equal to 2, as the definite integral from 1 to 2 of dx over x minus 2 to the 2/3, plus the definite integral from 2 to 4 of x minus 2 to the exponent negative 2/3 dx. And we break this apart into the limit. As t approaches 2 from the left, integral from 1 to t, x minus 2 to the negative 2/3 dx, plus the limit as t approaches 2 from the right of the definite integral from t to 4 x minus 2 to the negative 2/3 dx. And so we proceed by taking the antiderivative. We could do a method of substitution, but if we were to let u or m be x minus 2, then dm would be the same thing. And then we would have to change the bounds, and I'm going to avoid using the method of substitution here, since there is going to be no constant factor to adjust. So we're going to get x minus 2 to the exponent 1/3 divided by 1/3, which is times 3. And I'll do the other integral in green. So we're going to get the limit as t approaches 2 from the right, x minus 2 to the exponent 1/3 divided by 1/3, evaluated from t to 4. So we're going to get 3 times the limit as t approaches 2 from the left of t minus 2 to the 1/3, which is the cube root of t minus 2, minus 1 minus 2 is negative 1, and the cube root of negative 1 is negative 1. So minus a negative 1, which would become plus 1. And then plus 3 times the limit as t approaches 2 from the right. We get 4 minus 2, which is 2, and the cube root of that is the cube root of 2, minus the cube root of t minus 2. And in this case, if we look at the cube root graph with a horizontal translation of 2, maybe I can fit it in, I'll put it on the next slide. Y equals the cube root of t minus 2. It's going to be the cube root graph that we saw in the warm-up, moved 2 spaces over so that the vertical tangent occurs at t equal to 2. Now this could be called x, but I'm choosing to use t because that is my input variable. And so my cube root graph looks like this, with a horizontal translation 2 to the right, and as t approaches 2 from the left, y approaches a height of 0. I'm going to do that in blue because that's the blue integral, sorry, the blue limit. And as t approaches 2 from the right, y approaches a height of 0. And so we have this green limit is 0, and we have this blue limit is 0. And as a result, we get 3 times positive 1, which is 3, plus 3 times the cube root of 2. That's a finite number, and therefore this integral converges. Moving on to number 13, what values of p make integrals of the form definite integral from 0 to 1 of dx over x to the p converge? Well, this is very similar to what we were talking about earlier. We looked at several different graphs, and we talked about y equals x squared, and y equals the square root of x. Because later on we're going to be talking about their reciprocals, 1 over x squared, 1 over x to the 1/2, which are essentially functions of the form 1 over x to the exponent of p. And so we've taken a look at 3 different p values, or exponents on the denominator of x. We have p equal to 1, p equal to 2, p equal to 1/2. So we looked at the reciprocals, the original functions. And we know that when x is equal to 1, all 3 of these heights are the same. So in their reciprocal graphs, when x is equal to 1, all 3 of these heights are the same. Now let's broaden our graphs to be x greater than 0. In the original functions without 1 over, we know that when x is greater than 1, the x squared graph is the highest, the linear graph is the next, and the square root graph is the lowest. But on the interval from 0 to 1, those heights reverse. The lowest graph is the squared graph. The middle graph is the linear function, and the highest graph is the square root function. And so when we are looking at the graphs of the reciprocals, which graph, which color, red, blue, or purple, do you think will be the highest from 0 to 1? Because that's what this question is asking about on the interval from 0 to 1. Well, when x is equal to 1, all 3 graphs are the same height. When x is equal to 1 over here, all 3 graphs are the same height. Between 0 and 1, the red graph, the square root graph, is the highest, and the purple graph is the lowest. Blue is always in the middle. Y equals x is always the boundary between exponents that are greater than 1 and less than 1. So the reciprocal graphs will have the reverse behavior. And on the reciprocal graphs, the lowest will be the red, the middle will be the blue, and the highest will be the purple. And so if we just focus our attention from 0 to 1, we can see that it's kind of difficult. Maybe let's take a look at x equal to 1/2. If we just go up, and maybe I will set the range from 0 to 1, -1 to 4. We can see that the purple graph is the highest, the blue is the middle, and the red is the lowest, as we predicted the reverse order. Okay, but we actually want to find p from an analytical approach and the value of this improper integral when it does converge. So we know that the offending x coordinate, or the value of x that makes y undefined, is x equal to 0. So we rewrite the limit, the definite integral in terms of the limit. So it's the limit as t approaches 0, coming from the right, of the definite integral from t to 1 of x to the negative p dx. So I get the limit as t approaches 0 from the right of x to the negative p plus 1 divided by negative p plus 1, or 1 minus p, evaluated from t to 1. So we get the limit as t approaches 0 from the right of 1 in for x. Again, we know that p cannot equal to 1. So p equal to 1 is never allowed for an improper integral to converge of this form, whether the bounds are from 0 to 1 or from 1 to infinity, as we saw earlier. If p does not equal to 1, then this 1 over 1 minus p can come out in front, times the limit as t approaches 0 from the right, and we substitute 1 in for x, so 1 to the stuff is 1, minus t to the exponent 1 minus p. And as we just saw, if the exponent p is greater than 1 on this function, we are going to have greater than 1 is going to give us like a number of 2, 3, 4 for p. So if p is 4, we're going to get 1 minus 4. So this is t to the exponent negative 3. And the limit, if p is equal to 4, the limit as t approaches 0 from the right of t to the 1 minus p is equal to the limit as t approaches 0 from the right of t to the negative 3, which has a shape like this. And as t approaches 0 from the right on 1 over t cubed, y approaches positive infinity. Meanwhile, if we take p less than 1, like 1/2 or negative 3, or negative 4, or negative 1, or 0, so if we take p equal to 0, well, let's make it p equal to negative 1, just so that it doesn't seem like we're playing favorites with a number. Then the limit as t approaches 0 from the right of t to the exponent of 1 minus negative 1 is t squared. And on this graph, as t approaches 0 from the right, y approaches a height of 0. So for the different values of p that are less than 1, the heights approach 0 on this function. So this limit will diverge, not exist, if p is greater than 1, but if p is less than 1, this limit will be 0. And so we know that this goes to 0 if p is less than 1. And so we end up getting 1 over 1 minus p times 1 minus 0 is 1 over 1 minus p, where p has to be less than 1. So this integral will converge if p is less than 1. And it'll converge to the value of 1 over 1 minus p. That is consistent with what we saw in the graphs. We see that the red graph is going to be lower and therefore have a chance of being finite, while the purple graph is going to be higher and therefore has more area than underneath the blue curve, which definitely diverged because p can't be 1, because we get 1 over 0, which is undefined, before we even get to evaluate the limit part. In Math 152, we look at many different techniques of integration, but we do know that there are some integrals that cannot be integrated using any integration techniques, whether we have learned it yet or not. And so sometimes we can't integrate a definite integral, but we can still compare its value to another known definite integral. In the case of improper integrals, we can make conclusions about the convergence or divergence of an improper integral by comparing it, by its size, to a known convergent or divergent integral, or to other known convergent or divergent integrals. So the first comparison test is the direct comparison test. Let f and g be continuous functions on a domain 0 to a, or a to infinity, and we're going to let the height of g be greater than or equal to the height of f, which is non-negative. In other words, the height of f never exceeds the height of g. So if we have y equal to 0 as the lower bound curve, and f of x might be some graph that looks like this, well, to be general, it may touch but not go lower than the x-axis, and this is the f function, and then g of x is something like this on some interval from a to infinity. So then we say that if the definite integral from a to infinity of f of x dx converges, that will be true if we know the green function's definite integral converges. So if we know that the amount of green area is finite as x approaches infinity, then the amount of blue area, which is less than that, must also be finite. However, we will say that if the blue area is not a finite amount, then we know that the green area cannot be a finite amount. And so the integral from 0 to a to infinity of g of x dx diverges if the definite integral on the same interval of f of x dx also diverges. So we want to discuss whether integrals are integrals with finite bounds of all discontinuous functions improper integrals. Well, just because we have a discontinuity, it does not mean that we have an improper integral. For example, we can refer back to going back to Calc 1, we can recall the existence theorem for definite integrals. If a function is continuous on a closed domain, then the definite integral of that function on that domain definitely does exist. In other words, there's a finite amount of accumulation or definite integral for all continuous functions on a closed finite domain. However, we saw in that same section in 6.3 on definite integrals that even functions that have discontinuities, such as a removable discontinuity for the function f of x equal to x minus a times x minus b over x minus b, there's a removable discontinuity when x is equal to b, and if we take an interval on either side of that removable discontinuity, that there is a finite amount of accumulation. And so for a removable discontinuity, the definite integral does exist and is not considered to be improper. We can also take a look at a function with a jump discontinuity. And the standard jump discontinuity function is absolute value of x over x. And if we look at from -2 until 3, we can still come up with the definite integral, even though this function g of x is not continuous at x equal to 0. And so we get -2 times +2 times -1 is -2, plus 1 times 3 is 3, and so we have a definite integral of 1, even on either side, or the interval being on either side of the discontinuity, the jump discontinuity. So it's not true that all discontinuous functions have integrals with finite bounds that are improper integrals. So we're really specifically looking at discontinuous functions with infinite discontinuities or vertical asymptotes. So here we have a removable discontinuity, And here we have a jump discontinuity. And these are not improper. Okay, let's take a look at the integral from 0 to infinity of e to the negative x squared dx. We have seen as a common example of an integral that cannot be expressed in closed form any other way. We know that this does not have a closed form or simpler representation. Much the same way that when we see the square root of 2 or log base 3 of 10, that we cannot express these any more simply. We could approximate them using decimals, but these are irrational numbers who, in decimal form, with finite number of digits, would be approximations and not exact. If we had a definite integral, then we could evaluate this, let's say from 1 to 5, but we would have to use some kind of Riemann approximation method to approximate the value. And so the best way to refer to the number the square root of 2 is the square root of 2. Similarly, the best way to refer to the definite integral from 1 to 5 of e to the x squared dx is exactly that way. So in a similar way, we will not be able to use method of substitution, integration by parts, trig substitution or trig integrals, or partial fraction decomposition to rewrite and integrate the integral of e to the negative x squared dx. However, we're not really asked what is that value. We simply want to know, does that improper integral converge? And we can come up with the idea that x squared is greater than x when x is greater than 1. We can just look at the function y equals x and y equals x squared, and we can see that at x equal to 1, the two functions are at the same height, and then the parabola x squared heights are greater than x when x is greater than 1. So I'm going to be interested in taking my definite integral and breaking it up at x equal to 1. This is some finite value. It's a continuous function on a finite interval, so this is going to be some finite number. So now I'm going to focus on the definite integral from 1 to infinity of e to the negative x squared dx. And the reason I was comparing x squared with x is because I'm going to look at the definite integral of e to the negative x. So I'm actually going to compare the graphs. Let f of x equal e to the negative x, and let g of x equal e to the negative x squared. So when I consider these graphs, I do know what the graph of e to the negative x looks like. And I don't know what the graph of e to the negative x squared looks like. But I do know that x squared is greater than x when x is greater than 1. And so when x is greater than 1, e to the negative x squared will either be bigger or smaller than e to the negative x. So if I write this as 1 over e to the x, and I write g as 1 over e to the x squared, which function, the green one or the red one, do you think will be higher when x is greater than 1? Well, we know that x compared to x squared will be lower when x is greater than 1. And so e to the x will be lower than e to the x squared when x is greater than 1. But their reciprocals will be the reverse behavior. And so just to take a look at the graph of those two functions, the green one and the red one. I want to save that. X equals 1/2, and we'll look at that in the lecture notes. So if I look at y equals 1 over e to the x as my green function, and my red function is 1 over e raised to the x squared, I see that when x is greater than 1, the red function is higher, because we have the reciprocal, 1 over, but when x is less than 1, the green function is the higher and the red is the lower. And so as a result, we know that the green function will have a definite integral. Well, actually we don't, so maybe we do need to look at it. So let's consider, does the definite integral from 0 to x of e to the negative x dx converge? And I'm just going to make that in green. So we have limit as t approaches, rather this should be infinity, not x at the top. Limit as t approaches infinity of the definite integral from 0 to t, e to the negative x dx. And we consider the convergence or divergence of this improper integral because it is one that we can work out. So the antiderivative is negative e to the negative x, evaluated from 0 to t. And I'm actually going to change the bounds and multiply through by a negative. So we get e to the 0, which is 1, minus e to the negative t. And now we're going to look at the graph of y equals e to the negative t in order to evaluate the limit as t approaches infinity. This function looks like this. As t approaches infinity, y approaches a height of 0. So this approaches 0, and this limit is equal to 1. Because this integral converges, and as we saw in the graph, we'll put all of this in, we see that the green graph is going to be higher than the red graph when x is greater than 1. Our green graph converges all the way from 0 to infinity, and therefore the red integral will converge from 0 to infinity by the direct comparison test. So we say, since the definite integral from 0 to infinity of e to the negative x dx equal to 1 converges, and e to the negative x is greater than or equal to e to the negative x squared for x greater than or equal to 1, therefore by the direct comparison test, the definite integral from 0 to infinity of e to the negative x squared dx also converges. Had the higher graph diverged, we would not be able to say if the lower graph had an improper integral that also diverged. I didn't mean to say had the higher graph diverged, but had the integral of the higher function diverged. We don't know if the red graph, which is the e to the negative x squared graph, would have an integral that converged or diverged. We would need to compare with somebody else. Okay. The limit comparison test is another way to compare two functions or their definite improper integrals. If two positive functions f and g are continuous on the semi-closed interval from a to infinity, and they have the same rate of growth, that means the limit as x approaches infinity of their ratio is a finite number greater than 0, then either the definite integral from a to infinity of f of x dx and the definite integral from a to infinity of g of x dx both converge or they both diverge. So in number 15, we want to show that the definite integral from 1 to infinity of dx over 1 plus x cubed converges by using the limit comparison test. And we want to know what function's improper integral do we know that we can compare it to. Well, we know that 1 over 1 plus x cubed has a certain type of end behavior, and it will have the same end behavior as another function. Let's let f of x be the given function, and g of x be a simpler function whose behavior we know. Without the plus 1 here, we have a function 1 over x cubed, which is of the form 1 over x to the p, where p is equal to 3. And earlier in the video, we had seen that the definite integral from 1 to infinity of 1 over x to the p dx will converge, and it will equal a certain value for certain values of p. Take a moment to remember what they were and write down the result here. This result is 1 over p minus 1, where p is greater than 1. And so we can compare this, we can recognize that this is the case when p is equal to 3 for the g of x function. Therefore, the integral from 1 to infinity of 1 over x cubed dx is equal to 1 over 3 minus 1, which is equal to 1/2. And so the g of x function has a definite integral, or an improper integral, that converges. Now what we need to do is confirm that f and g have the same rate of growth, and therefore by the limit comparison test, the definite integral given for the f of x function will also converge. So to compare the rate of growth, we need to evaluate the limit as x approaches infinity of f of x over g of x. We could also do g of x over f of x. It wouldn't matter which one we put on top. Let's say that the limit of f over g is equal to 2. Then the limit of g over f is equal to 1/2. Both of those results of 2 or 1/2 satisfy lying in between 0 and infinity. So it doesn't matter which function that you put in the top and which one you put in the bottom, because we are comparing that there is a finite rate of growth. In other words, that these two functions have a similar type of end behavior, plus modified by a scale factor or a vertical scale factor, a constant. So I'm going to see, if I put the f of x in the top, I have 1 over 1 plus x cubed divided by 1 over x cubed. Works out to be the limit as x approaches infinity, and then instead of dividing by 1 over x cubed, I can multiply by x cubed. And here, if we go back to pre-calculus, we're talking about the zoomed out behavior on the right-hand side of the function x cubed over 1 plus x cubed. We can predict, because we have the same degree of the polynomial on the top as in the bottom, we can predict that we will get a constant quotient, which means that this function, x cubed over 1 plus x cubed, has a horizontal asymptote. Let's just take a look at what the graph means. What that limit means as a graph, rather. So if I take a look at a function y equals x cubed over 1 plus x cubed, then when we zoom out far enough, eventually, and we turn off the axes, eventually we see a horizontal asymptote. And that horizontal asymptote is at a height of y equal to 1. That, of course, is just the quotient when we divide the numerator by the denominator. And so this limit is equal to 1, and 1 is a finite number greater than 0 and less than infinity. So therefore, by the limit comparison test, we know that our unknown function with unknown integral behavior and our function with known integral behavior that does converge have the same rate of growth, and therefore the given integral converges. To what? How much it is, we don't know, but we do know that it converges. Okay, the last example says to show that the solid generated by revolving the curve f of x equal to x times e to the negative x of infinite length, meaning we're going from x equals 0 forever towards x approaching infinity, that there will be a finite volume when we revolve the curve around the x-axis. So we go back to 7.3 and we look at volumes of revolutions, and we need to set up an integral. We can recognize cross sections here, and in the cross section we have a radius for the circular cross section. Here we have a point x comma y, which has coordinates. When x is x, the y coordinate is called x e to the negative x, and therefore the radius is going to be y top minus y bottom for that length, y bottom at that point is a constant of 0, and so we end up getting the radius is equal to x e to the negative x. So take a moment, set up the volume, and see how it fits into 8.9 improper integrals. Going back to basics, we know that volume is equal to the integral of a little bit of volume, which is going to be area multiplied in this case by the thickness, which is a dx. The cross-sectional area is that of a circle that has a formula of pi r squared. Taking the pi outside and squaring the radius and interpreting the bounds from 0 to infinity gives us an improper integral. So I'll leave you to apply techniques of integration along with rewriting this improper integral as a limit and seeing if the limit exists to determine the finite volume of pi by 4 and therefore confirming that this improper integral converges. Well, that concludes section 8.9, improper integrals. Please make sure that you have completed the handout and prepared a list of clarifying questions about the lecture. That's all for now.